Have you ever really looked at a wire? I mean, it seems like the simplest thing in the world, right? Just a piece of copper with some plastic around it. But what if I told you that whole simple wire thing is kind of a lie? That it's actually a super complex, high-stakes system engineered with the same precision as a spacecraft. Okay, let's get into this, because the science behind how we connect things is way more interesting than you think.
And when I say high stakes, I am not kidding. This isn't just some abstract theory. We're talking about real-world catastrophes, like the disasters of TWA Flight 800 and Swissair 111. In those cases, degraded wiring led to sparks and, tragically, the loss of the aircraft. Those events forced the entire engineering community to hit the reset button and completely rethink something they had always taken for granted.
So that's the big question, isn't it? How can a basic strand of metal be so complicated and, sometimes, so unbelievably dangerous? Well, the answer is in all the invisible forces and hidden stresses that every single wire is constantly fighting against, 24/7.
To figure out how to build a wiring system that doesn't fail, engineers first had to become masters of how they do fail. And it turns out, every wire is living in a really hostile environment where it's under a constant three-pronged attack.
These are the three big enemies. You've got electrical stress, which is when the voltage itself is high enough to just punch through the insulation. Then there's thermal stress, where the current flowing through a wire generates its own heat, enough to melt itself. And finally, good old mechanical stress. We're talking vibration, sharp ends, and chafing that can literally tear a wire apart from the inside.
Let's start with the spookiest one, that invisible electrical stress. We're going to talk about taming something called electromagnetic interference, or EMI. Think of it like a ghost in the machine, and if you don't get it under control, it can cause absolute chaos.
So here's the core idea you need to get. Every single wire, whether it's in your car, your computer, or a 747, is acting like a tiny little antenna. Some of those wires are broadcasting electrical static, just shouting it out, while others, more sensitive wires, are trying to listen for a clear signal, and they're picking up all that noise instead.
And here's a cool way engineers think about this. They turn the wires into characters. On one side, you've got the aggressors. These are your high-power wires, especially ones that switch on and off really fast. They are just screaming electromagnetic noise. And on the other side, you have the victims. These are delicate little signal wires carrying sensor data, and they're trying to whisper. Now, you can imagine what happens when you put a screamer right next to a whisperer. The message gets totally lost. So how seriously do they take this separation? Oh, it's a huge deal. Just look at this NASA standard. If you've got a high-power wire running next to a sensitive radio cable for more than just 5 feet, they have to be separated by almost a full foot of empty space, 11.8 inches. That is a massive amount of real estate inside a tightly packed rocket, and it just goes to show you that distance is your best friend when you're fighting this invisible enemy.
Okay, but what if they have to cross paths? You can't always keep them that far apart. Well, it turns out there's a wonderfully elegant solution. You make them cross at a perfect 90-degree angle. See, at that specific angle, the magnetic field from the power wire runs parallel to the signal wire, so it can't induce any noise. The aggressor literally becomes magnetically invisible to the victim. It's brilliant.
All right, so we've handled the electrical ghosts. Now let's get back to the physical world, because the enemies of heat and mechanical stress are very, very real. Now here's a concept that really messes with people's intuition, the thermal trap. You'd think, okay, this wire is rated for 10 amps, so it can carry 10 amps. End of story. But nope, that's not how it works at all. When you start bundling wires together into a harness, they act like a thick thermal blanket. The wires stuck in the middle have no way to get rid of their heat, so they get way hotter, way faster than a single wire hanging out in the open air.
And the effect of this is it's staggering. One wire all by itself, sure, it can carry 100% of its rated current, no problem. But put that same wire into a bundle of just 15 wires, and suddenly its safe capacity drops to about 58%. And in a big bundle of 30 or more, you're down to around 45% of what it says on the box. Ignoring this is one of the top reasons wire harnesses overheat.
And what about that mechanical stress? Well, here's a simple rule of thumb that prevents countless failures. The 10x rule. For any wire that's not designed to constantly flex, you can never, ever bend it tighter than 10 times its own thickness. If you do, you start to create tiny cracks in the insulation, and you fatigue the copper inside until eventually it just snaps. Simple rule, but absolutely crucial.
So now we have to talk about the single most vulnerable part of any wiring system. And guess what? It's usually not the wire itself. It's the end, the connection point. That is where the vast majority of failures happen.
In the worlds of aerospace and automotive, the gold standard is the crimp. A perfect crimp actually cold welds the wire and the terminal together. It mashes them into a single solid piece of metal that's called gas tight, because there are literally no air gaps for oxygen to sneak in and cause corrosion. But if you get it wrong, if you undercrimped it, you create resistance, which means heat. If you overcrimp it, you make the metal fragile, and it'll just crack under vibration.
So you might be asking, why not just solder everything? Isn't that easier? Well, no, because of this really sneaky problem called solder wicking. When you solder a wire, the molten solder can get sucked up into the copper strands underneath the insulation. And what that does is it turns a nice flexible wire into a solid, rigid rod. And right at the point where that rod ends, you've created a perfect spot for it to break. Add a little vibration, and snap, the wire breaks clean off.
And this obsession with detail goes right into the design of the connector itself. I mean, designers have to keep high voltage and low voltage pins far apart from each other to stop sparks from jumping. They'll put the pins that carry the most current on the outside of the connector, where they can get some airflow and stay cool, and maybe most important of all, they use different physical shapes, or keys, so that it's physically impossible to plug the wrong harness into the wrong socket, which could literally fry an entire system instantly.
So when you put all these pieces together, what does it all mean? It means that building a proper, reliable wiring harness isn't just about connecting point A to point B. It's a genuine science. It's about engineering a system to fight back against the fundamental forces of physics and chaos. And that brings us to what might be the most profound, most important lesson from all of professional electrical engineering. We all think a fuse or a circuit breaker is in our house to protect our expensive computer or our TV. But you know what? That's its second job. Its first, its primary, its most important job is to protect the wire inside the wall. It's designed to trip long before that wire gets hot enough to start a fire. The safety of the wire always comes first.
So, from invisible magnetic fields and thermal traps, all the way down to the metallurgy of a single tiny crimp, there's a whole world of hidden genius packed into that humble wire. The next time you go to plug something in, just take a second look at that cable. It's not so simple after all, is it?